Hi everybody, can you hear me?
Yes, sir.
Yes, sir.
Okay. Hi, welcome to this live session in NPTEL of this course, Basic Reanalysis. Okay, so first let me introduce myself. I am Shovik from IIT Madras Mathematics Department. Right now I am doing research in pure mathematics. Okay, so in this live session it will be a 2 hour live session, and in this session our main target is to solve some kind of problem. I mean, problem solving is the main motivation of this live session, and obviously if you have any doubts any problems in the concept, so you can tell me. I will try to solve as much as possible. Okay. Someone is one second. Yeah, so it will be 6 to it is from, so well, it is now 6 p.m., so the live stream will continue up to 8 p.m. Okay, so first one second. So first 1 hour will be consist on problem solving. Then you can tell me your problems, your doubts. Uh, if then time remains, then we will again start solving problem. Okay. So just sorry, any one of you, can you please tell that till now what has been done in your uh, reanalysis course in the NPTEL? Hello, can anyone hear me? Hello, can anyone hear me? Anybody tell?
Yes, sir. I think
Yes, sir.
only till definition of sequence and I think convergence.
Okay, so definition
Let
is
me check
convergent.
again.
Okay, okay, I understand. So till now, nothing regarding. One second. Just one second. Let me share the screen here. One second. So till now, sorry. Till now, nothing regarding that supremum infimum has till now has it been done, or only sequence has been done.
Basic part of sequence.
Okay, okay, I understand. I understand. Okay, so okay, so today we will start solving problems from the sequences. Okay, so just before starting, let me know one thing about that. Only sequence has been done, or the subsequence thing? Yeah, subsequence has been done or not?
No, no, it is not done.
Okay,
No
I
subsequent.
understand. Okay, thank you, thank you. So okay, so let's start. Okay, so we will start from very basic problem, then gradually we will do us a little bit difficult steps. Okay, so let me present. One second. So can you see my screen?
Yes, sir.
Okay, okay. Just wait a second. Okay, um, so first question is that show that the sequence 1 by n will goes to 0 and tending to infinity. By the way, before starting, let me ask you one thing: is that handwriting is okay for you? I mean, is do I need to write in a larger way, or this format is okay?
Okay, sir.
Okay, thank you.
Sir,
So
it's okay.
For format is okay. If you can switch the background to white, it might be better, and writing to be black.
I understand. One second. Let me change it. Second. Yeah. Now everything okay?
Yes, sir.
Yes. Okay. Okay. I understand. So so just show that this sequence 1 by n will converge to 0. So can anybody give me some idea how to solve this type of problem? I will also solve, no issue, but anybody can give some idea. I mean, it's a discussion type of thing, right? So we can discuss, then we can get the final answer, right? So anybody tell me? Anybody? One second. Anyone for audience who's waiting here? Yeah, anybody tell me how to?
Yes,
Sir,
Hmm. Yeah, tell.
so when we are putting natural numbers in place of college, like one, two,
Probably wait,
and
wait.
so on.
Probably more than one is speaking, so just any of one tell. Okay. Otherwise, it is I can't hear properly actually.
Yes, when we are putting the camera, it is like going on 60 things and it's
Yes, yes.
changing to 100 actually.
Right, right.
And
Yeah.
if we point out in number 9, we can say that also.
Yes, yes. Is correct. So, how to solve it? Okay, um, so formal ways we need to choose a epsilon greater than 0. Okay, one second, someone is trying to enter. So the choose epsilon greater than 0. Okay, so now the point is by Archimedean property, there exists a k belongs to n such that 1 by n is less than epsilon for all n greater than equal to k. So by definition, I mean, sorry, this 1 by less than epsilon, we can write it in a modified way that 1 by n minus 0, this is less than epsilon, 1 by n greater than equal to k. So then the sequence 1 by n goes to 0 as n tending to infinity. Okay. So obviously it's a very basic one. Everybody, each and everybody can understood this, can understand this solution. I understand it's very basic, but if anybody has doubt, kindly ask me. I will explain it to again. Okay. So let's go to the next problem. So one second, let me go down. One second, someone is trying to join. So prove the following. We have the following question. Prove the following. Uh, if 0 less than a less than epsilon for all a greater than 0, then show a equal to 0. So can anybody tell how to solve it?
Sandwich theorem.
Sorry, which theorem? Sandwich.
Sandwich theorem.
Yeah, it can be done using sandwich theorem. Uh, yes, yes, it can be done, but what are the basic way? I mean, sandwich theorem is something is sandwich theorem is sufficient.
One way we can prove by contradiction.
Yeah, right. Yeah, that's okay. So 0 less than equal to less than 1 by n for all n. Taking limits both side. So a equal to 0. Yeah, very good. So next problem is what is the limit n tend to 3 square. Now how to solve this problem? I mean, I understand that this limit can be computed using the method that we have all learned in the class 12, okay, but the point is how to prove this limit is 3 using the definition of the sequence. I mean, using definition of convergence sequence, how to prove it. So let's start. Okay, so we all know it is the limit is 3, but we need to prove it. Okay, so let's do the following way. So this is what this will be 2n minus 2 by n square plus this is what this is equal to 2 into mod n minus 1 by n plus 1. One second. Sorry. So so this can be written as 2 into n by n square plus 1 plus 1 by n to n square plus 1. Okay. Now obviously n less than equal to n square, so this is less than equal to 2 into n square by n square plus 1 plus 1 by n square plus 1 as n is less than equal to n square. Okay. So so obviously this is less than 2 plus 1 by n square plus 1. Okay. Now obviously this is less than epsilon for all n less than equal to for sufficiently large scale. Oh, one second, someone is trying to join actually. Yeah, so in this way you can, one second. So in this way you can show that this limit is actually 3. Okay. So obviously this is a very basic way. So there another problem is that, okay, by the way, let me tell you one thing that this meeting is being recorded, so you don't need to worry about any internet disruption. Okay, this meeting will be uploaded in the YouTube and you can all see it will be publicly available. Okay, so the following question that find the limit n into infinity root over n plus 1 minus root over n. Sorry. Can anybody speak up how to solve this type of problem?
Rationalization.
Yeah, right. So, sorry, it's my mistake. So as is suggested, when it once someone is trying to join. Yeah. So what I have done. Sorry, that's it. Sorry, I made a mistake actually. So So this will be just 1 by root over n plus 1 plus root over n, which goes to 0 and tending to infinity. So this limit is 0. Yeah, right. Now, so you must have learned that sandwich theorem, because initially someone has used that, right? Everybody know sandwich theorem? Yeah, okay. So we have one nice problem. Let me open my page. Yeah. The problem is that find the following limit. What is that? Prove that limit 1 by root over n square plus 1 plus 1 by root over n square plus 2 plus dot 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 1 by root over n square plus n. This is equal to 1. Okay. One second, someone is trying to enter. Yeah. So how to solve this type of problem? So here obviously we need to use the sandwich theorem. So let's see how can we use it. Okay. So obviously using the sandwich theorem is a matter of trick. Okay. So let us see. So someone is trying to join. Well, observe that root over 1 by 1 by root over n square plus 1, this is less than equal to sorry, this is 1 by root over n square plus 2, this is less than equal to root over n square 1 by root over n square plus 1. 1 by root over n square plus 3, this is less than root over 1 by n square plus 1. So all these 1 by root over n square plus n is less than root over 1 by root over n square plus 1. Okay. So then so so just add all this. So 1 by root over n square. Sorry.
ஸ்வாதி சைஸ் எது கரெக்டா இருக்கும்
Sorry, sir. Can I speak? I couldn't hear you properly.
எம்
Yes. Which line of this? Which line? For second or third line?
நீ எது எடுப்ப டபுள் எக்ஸ்எலா அப்ப எக்ஸ்எல் கரெக்டா இருக்கும் தானே
Hello. Sorry, I could not hear properly actually. Hello.
அக்காக்கு தான்
Hello. Well, one thing is that probably there is a network interruption. So can you please write your question in the chat? Then I can answer, because probably voice is breaking. Okay. Hope you understand. One second. Someone is trying to join. So now so add up all this. So this will be 1 by root over n square plus 1 by plus root over 1 by n square plus 2 plus and dot 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 root over 1 by n square plus n. This is less than so it will be n terms, so n by root over n square plus 1. Wait, someone is trying to join.
Sir, will we get recording of these live sessions?
Yeah, this will be uploaded on YouTube, and from NPT you will get the recordings. No issue. Okay.
Okay, thank you, sir.
Yeah. So this will be the one side. So this is the equation 1, and for the second equation, observe the following, that Yeah, for the second equation, for the it's a for right side we have get us inequality, and for the left side we need to use the following tree. There is 1 by root over n square plus 1 by root over 1 by root over n square plus 2. This is greater than 2 by root over n square plus 2. Okay, and similarly we can extend this as following: 1 by root over n square plus 1 by 1 by root over n square plus 2 plus 1 by root over n square plus 3. This is greater than 3 by root over n square plus 3. And one second. Similarly, dot dot dot, we can ultimately prove that this 1 by root over n square plus 1 plus 1 by root over n square plus 2 plus 1 by root over n square plus 3, it is greater than n by root over n square plus n. Okay, so this is the equation 2. So once again, so if we call this whole sum to be un, so equation 1 and equation 2 together gives n by root over n square plus 1 less than un less than n by root over n square plus 1. Now you can check that this goes to 0 and this goes to 0 as limit n tend to infinity. So by Sandwich theorem, limit n tend to infinity un equal to 0. Okay, so in this way you can actually solve this problem. Related to Sandwich theorem. Okay, so let me repeat this problem once again. If nobody, just tell me one, let me tell you one thing. If anybody have any issue in these problems, kindly ask or kindly type it over the chat. I will answer it. Okay, so the method of the the Sandwich theorem is okay, but the problem is that how you can solve. Okay, this solution actually shows you a trick by which you can solve this type of problems by showing that this summation thing is less than something and is greater than something, and you need to check that both limits on the left and right side are same. Then you can directly use the Sandwich theorem. Okay, so sorry, there it's my mistake. It will be both limit will be 1. Sorry. So, yeah, wait, someone in a chat probably. One second. One second. Yeah, so there is a chat somehow saying yeah, so Shoham, yeah, I'm going to explain this Sandwich theorem. Let me no issue. Yeah, so one second. So so the statement of the Sandwich theorem as follows: let un, vn, wn are three sequences of real numbers, of course, and suppose there exists m natural such that we have the following relation: un less than vn less than wn for all n greater than equal to m, and let limit n tending to infinity un is equal to l is equal to limit n tending to infinity wn. So the Sandwich theorem tells that limit n tending to infinity vn is equal to l. Yeah, so this is a statement of the theorem. So it's like, suppose we have a two sequences un vn, and there is some in between sequences to vn. Sorry, one second. So we have two sequences un, vn and wn, and if vn is actually in between un and wn after certain n, then the Sandwich theorem tells if both the limits of un and vn are same, then un and wn are same, then vn, the limit of vn will be same. It's like vn is has to be sandwiched between the u and w. Yeah, that's the statement actually. There is really nothing much more to say. So Shoham, do you understand the theorem, statement of theorem?
Yes, sir.
Okay, okay. So one second, there's some another chat. So Prince, Prince, yeah, Prince Pandey. So which portion you couldn't understand? I will explain it to you again.
Sir, there is very problem in this.
Yes. Yeah. Which problem? Just tell
Sir,
me.
I cannot connect.
Sorry.
Sir, I cannot connect clearly.
I mean, uh, so you were talking about any disruption or something like that.
No, sir.
So I mean, tell me your problem.
Sir, you are.
Sorry, I could not hear you. Can you please repeat?
Sir, you study very fast, and I cannot connect all
Yes,
the
yeah.
topics
Okay,
because.
okay, okay. Yeah, 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 I understand. Oh, sorry, sorry. I mean, yeah, okay. So, no issue. Okay. Now I'm going very slow. No issue, no issue. So, once again, so do you understand the first problem that the sequence 1 by n goes to 0?
No, sir.
Okay, so, let's go back to definition here. First, tell me one thing. Sorry, first, let me tell one, let me, first, you can tell me one thing that, what is the definition of a convergent of a sequence? Suppose you have a sequence xn and sorry, one second, someone is trying to join. Yeah, so Prince, tell me one thing. What is the definition of a sequence xn converges to limit L?
Sir, a sequence n is said to be convergent. Sequence converges to a is element of R if for any epsilon is greater than 0 be a real number. There exists a positive integer m such that n, uh, n is greater than or equal to m. This implies a mod of n minus a is less than uh, less than epsilon. Sir,
Yes, you are right. Now tell
sir,
me
sir,
which line.
I cannot feel it.
Oh, you can feel it. Okay, okay. Oh, yeah, I
Sir,
understand.
I cannot feel it.
Yeah, I understand. I understand. I understand your issue. One second, let me go down actually. So, what you've said that is an minus a, this is less than epsilon for all n greater than or equal to after something. Okay. So, this is like, I mean, pictorially, it is pictorially, it is like, so you have a sequence, you have a point A somewhere. Okay. So, you have some points A1, A2, AN. Okay. By default, I am taking the sequence to be increasing because, I mean, in order to give some kind of intuition. Okay, it's a just intuitive thing. So a1 into n sequence, the point is that this equation says what mod an minus a less than epsilon is what actually it is. um yeah, it is an minus, sorry, it is a minus epsilon less than an less than a plus epsilon. So this means that
Yes.
for all n greater than or equal to k, this holds. Okay, this means that we can find a small neighborhood around a where the all the terms of the sequence an will lie after a particular integer k. Okay, so in this neighborhood we can find all the terms ak plus 1, ak plus 2, ak plus 3, dot dot dot. Okay, I mean,
Yes, sir.
obviously, this neighborhood can be very small because epsilon is arbitrary. We can choose it as much small as we can. Okay, so the moral of the story is the sequence converges to a point means around that point, if you can choose a very small neighborhood, within that neighborhood you can get infinitely many. I mean, you can get infinite number of points are in that neighborhood of that sequence. So then in this type of case, we say that sequence converges to that point. Okay. Now I understood the point. I mean, you get, can you got some kind of feeling?
Yes, sir. I can understand little bit.
Okay, okay. So, one second. So let's start with the first problem that we have discussed, because it might be that Prince has some issue with it. So now let's prove that the sequence 1 by n converges to 0. So Prince, tell me one thing, how we can prove that 1 by n goes to 0. Prince, hello.
Yes, sir.
Yeah, yeah. Just tell me how you can prove 1 by n goes to 0.
Sir, let a equal to 0
Yeah, a equal to 0, yes.
and let epsilon equal to 1 by 20 and
No, 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 no. First,
uh,
no, no. The first point is that the definition of the sequence of convergence, so in the definition of the convergence sequence, the epsilon greater than 0 is arbitrary. Okay, means what? The arbitrariness.
arbitrary.
Yes,
Yes, sir.
yes, yes. So you can't choose any particular number. You can only choose epsilon greater than 0. It is a very arbitrary number. The arbitrariness of this epsilon gives that, I mean, only gives us the freedom that we can choose very small neighborhood around a, where the sequence, the terms of the sequence can lie after finally many terms. Okay, so we choose the epsilon greater than 0 arbitrary. Now then how we can proceed? Tell me, Prince.
Then sir, mod of a 1 upon n minus
Yes.
n minus 0
Yes, right.
is greater than 0, less than 0.
No, sorry, 1 by n less 1 upon n less than 0. I mean, what? It doesn't make any
1
sense.
by n minus 0 equal,
Yes.
less than 0.
No, no.
Hmm.
First is a mod. Like modulus of 1 by n minus 0 can't be less than 0, right? Because it is a modulus, and here it is 1 by n. So anyway, this term is positive, right? So this thing
Yes,
doesn't
sir.
make any sense, right? So according to definition, what we have to do? One second, someone want to join actually. Yeah, so Prince, yeah. So according to definition, what we need to show? We need to show that 1 by less than 0. This is, sorry, 1 by minus 0. This is less than epsilon for all f. This is less than epsilon for some n, for all n greater than or equal to k for some k, right? According to the definition, we need to show. If we can show this, then we are done, right?
Yes, sir.
Yeah. So now tell me how you can. So we need to show 1 by less than epsilon for all n greater than or equal to k for some integer. Now tell me how you can prove it. I mean, how you can find this capital K. Okay. So since you are doing it, you are learning it for the first time. So let me do it from you in the another way. Okay. So we need to show 1 by less than epsilon. Okay. So this implies what? This can happen if and only if n greater than 1 by epsilon, right? So
Yes, sir.
choose k equal to box 1 by epsilon plus 1. Do you know box function? This is box 1 by epsilon. Do you know this?
No, sir.
Well, so once again, sorry. Well, so box is like if box x is equal to sorry, box x is equal to one second. Box x is nearest integer to x less than or equal to x. This means if it is x, then the nearest integer which is less than or equal to x is said to be box x. So box 2.5 is 2. I mean, it is example, and box
Yes, sir.
0.5 is 0. Okay, so this is the box function. So
Yes, sir.
so anyway, box some, so obviously, I mean, so by definition box x is anyway less than equal to x, right? Okay, so if we choose k equal to mod 1 by epsilon plus 1, then we can do what? We can say that n is less than, sorry, 1 by n is less than epsilon for all n greater than equal to k, right?
Yes, sir.
Yeah. So we need, actually we want to prove this 1 by n less than epsilon for n greater than k for some k. We get our k. So 1 by n goes to 0, right? You understand the whole way out of the solution?
Yes, sir.
Okay, okay. So one second. Well, there is some chat is there. One second. Well, some one learner named Joby McRae asked me to explain the limits. Oh, well, I will explain before that I have solved the problem of Prince. Okay. So Prince, what about second problem? To understand the second problem, that is 0 less than equal to a less than epsilon, we need to show that a equal to 0. Do you understand this? One second, someone is trying to join actually. Yeah. Prince, so what about the second problem? Do you understand this? Or if any issue, tell me.
Sir, I take time, so then I can understand this. I can see the recorded video for
Yeah, yeah,
understanding.
yeah, yeah. You can ask me in the next week, this Friday, okay?
Okay, sir.
Yeah. Okay.
Sir, I have
So,
a doubt that we have been given 4 sessions. Are all these 4 sessions same or different problems will be given?
yeah, yeah, there are 4 sessions. So the 4 session will be taken by four people. Okay. So it depending on him or her what he will or she will do. Okay. Actually, I don't know about it. Okay.
Okay, okay.
Hello, sir.
Yeah.
I have a doubt in the third question.
Yeah. Sorry. Once again. Which one? Third one? Yeah. That
Third
will be
question.
it.
Yes.
3 and
Yes,
square
yes,
root.
sir.
Yeah.
Yes. You are writing there that 2 into mod of n minus 1 upon n square plus 1. So
Yes.
2 is multiplied to whole. So why you are writing there 2 into n upon n square plus 1 plus 1 upon n square plus
Yeah,
1?
yeah, yeah,
Why
yeah,
is
yeah.
not there
Right,
2
right,
upon n
right,
square
right, right,
plus
right,
1?
right, right, right. Thank you, thank you. It's my mistake. Thank you very much. Yeah. So everywhere it will be 2, right? So now this is correct? Yeah, I think so.
Yes, sir.
Yeah, okay, thank you. Wait, someone is joining. One second. So, somebody was here asking me to. So Joby McCauley asked me to explain that limit value. Okay, so let me explain it once again. So Joby, can you please tell me actually in which line you have the issue or you couldn't understand the whole solution? Hello, Joby, are you there?
Can you please show the step where you are breaking the mod, like mod in -1? That
In the previous problem, right?
yes,
Yeah,
yes.
this
Can
3
you
and
explain that step bit? That how are you breaking n-1 to n+1 like that? Okay, you attended it
oh,
already.
understand, understand.
Thanks,
Okay,
sir.
okay. So basically, your question is that how this step is doing, right?
Yes, sir. Yes, sir.
Yes, yes.
I got it that it's greater
Yeah, there
than
is a
zero.
formula na that mod a minus b less than equal to mod a plus mod b, right? So using this, I can do it, right?
Yes,
Okay.
yes, yes.
Wait, someone is trying to join. One second. So, one second. Who was here to ask the question actually? So, Jobby, are you there? Hello, Jobby, are you there? Probably he left. Okay. So, let's solve another problem once again. Yeah. So there is a interesting question that is I mean, it is not. It is a very basic, but yeah. So show that un goes to 0 if and only if the sequence mod un goes to 0. That is, we need to show that if we have a given sequence un, it will go to 0 if and only if the modulus sequence will go to 0. So can you tell me how to solve it? Well, first let me give the hint. The hint is that we need to use that mod of mod a minus mod b less than equal to mod of a minus b. That's it. This need we need this sorry this hint we need to use. So now can somebody try? You can take your time, no issue. Well, so since no one is responding, so I am solving this problem. Okay? So
Can we substitute A by UN and B by 0, something like that?
you are right. Very good. So let me write it down. So since un goes to 0, this so for any epsilon greater than 0, mod un minus 0 less than epsilon for all n greater than equal to k, right? So this implies what? This implies mod un less than epsilon for all n greater than equal to k, right? Now mod of mod un minus mod 0. This is what? This is obviously mod un, right? Now obviously this is less than epsilon for all n greater than equal to k. So this implies what? This implies the sequence mod un itself goes to 0 as n tending to infinity. So everybody understood the proof? Anybody have any confusion or problem? So I think there is no confusion. Well, anybody has any confusion, please ask. Okay. So this is the one way. I mean, this is the one side solution. The second side is that we need to show. So assume in a second situation, assume the sequence mod un goes to 0 as n tend to infinity. So choose epsilon greater than 0. So since the sequence mod un goes to 0, so mod of mod un minus 0, this is less than epsilon for all n greater than equal to k. Obviously for some k, right? It is the definition. So this implies what? This implies mod of mod un, this is less than epsilon for all n greater than equal to k for some k. Now this is mod of mod un, this is obviously mod un. So mod un less than epsilon for all n greater than equal to k. This implies what? This implies mod un goes to 0. Sorry, this implies un goes to 0 as n tending to infinity. So we are done. So anybody have any confusion or doubt in this second part of this problem? Okay, so I think everybody is okay with the solution. So, one second. Well, there are some other kind of problems we need to solve. One second. Okay, so um, prove the following that prove that limit n to infinity n to the power 1 by n is equal to 1. Can you tell me how to prove it? Anybody can try. Anybody? Well, so yeah, it's a non-trivial problem. So let me prove it. Okay. So observe that since n to the power 1 by n, this is greater than 1 for all n greater than 1. So we can write n to the power 1 by n is equal to xn plus 1 for all n greater than or equal to 1. Okay. So then n equal to xn plus 1 to the power n. Yeah. So this can be written as, so now we need to the binomial expansion. Sorry. This will be 1 plus nxn plus n into n minus, 1 by 2 xn square plus dot 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 xn to the power n. Okay. So this is greater than 1 by 2 into n minus 1 xn square. Okay. So this is the basic calculation. So finally, after the calculation, we get that n is greater than n into n minus 1 into xn square by 2. Okay. So this is the first step. In the second step, in the second step is also tricky. Here, observe that xn square is less than 2 by n minus 1 for all n greater than 1, right? So this implies what? Mod xn less than root over 2 by root over n minus 1. Okay. Now, you can use the Sandwich theorem. How? That is root over 1 by 1 by root over n minus 1, this goes to 0. So this limit, so this implies the sequence xn goes to 0. Okay, as n tends to infinity. Now, since n to the power 1 by n is equal to 1 plus xn, and as the sequence xn goes to 0 as n tends to infinity, so the sequence n to the power 1 by n goes to 1 as n tending to infinity. Okay. So in this way, we can solve this type of problems. Has everybody understood this problem?
Yes, sir.
Okay. So, one second. So there are some other questions I have. So, one second. An issue with my driver actually. You will just hold a second. There is issue with my driver. Okay. Now it is okay. So huh. So the second problem that we need to solve is that, yeah, the problem, the question is that prove that limit r to the power n equal to 0 for mod n less than r.
First,
So,
we have strings on
sorry,
feasible.
screen is visible. Oh, so one second. Sorry. Sorry, there is some issue was going on. That's why. Sorry for the inconvenience. Yeah, now we can see, right? Now we can see, right? Yeah. Okay. So we need to prove that limit rn equal to 0 mod for our r with mod r less than 1. Okay. So how to solve this problem? So yeah. So since mod r less than 1, we can choose, I mean, r may be equal to 0, right? So if r equal to 0, what the sequence r to the power will be? It will be like 0, 0, 0, 0, 0, 0, dot, dot, dot. Okay. So for r equal to 0, this is not the matter of concern. Okay. So if r not equal to 0, but mod r less than 1, it is the matter of concern. Okay. So if mod r less than 1, this implies what? This implies 1 by mod r greater than 1, right? So obviously one thing do note that the calculation of limit involves some kind of trick, okay, and we need to get used to all these type of tricks. Okay. So 1 by mod r greater than 1. Once again, someone is trying to join. So 1 by mod r is greater than 1. Okay. So let 1 by mod r is equal to a plus 1, while a is greater than 0. Wait, someone is trying to join again. So it is a greater than 0. Okay. So now observe r to the power n minus 0. This is mod r to the power n. This is equal to mod r whole to the power n. This is equal to 1 by 1 plus a whole to the power n, right? So what we see is that, wait. So this 1 by 1 by a to the power n, okay. So this much we get now. So now observe that 1 plus a whole to the power n, this is greater than na for all n belongs to n. Okay. So r to the mod of r to the power n minus 0, this is less than 1 by na for all n belongs to n, right? So choose a epsilon greater than 0. So this gives a what? So then mod r to the power n less than minus 0 less than epsilon, this holds if and only if n greater than 1 by a epsilon. Okay. So choose our k to be 1 by a epsilon plus 1. So then we can see that mod r to the power n minus 0, this is less than epsilon for all n greater than or equal to k. So this sequence Rn goes to 0 when mod r is less than 1. So we are done. So anybody have any issue with this question? Tell me.
Sir, how is mod r to the power n equal? Means how is r to the power n, which is within the mod, is next step replaced by mod r to the power n if means r is not safe to be positive?
You are right. Hmm. Second.
R is not equal to 0, no?
Yeah, you are right. So yeah, so we need to here assume some extra condition that r is greater than 0. Okay, you are right. Sorry, greater than equal
Sir,
to.
r is not equal to 0 is already given there, no?
R not equal to 0. No, no. I mean, in the question is we need to show Rn equal to 0 for mod r less than 1. Right? So R can be equal to 0, right?
Okay.
Yeah. So yeah. So this is the same problem. What's that? No, one second. So there is another problem which says that well, wait, someone is trying to join. So this problem, the question is that yeah. So if we have some a greater than 0, then show that limit n tend to infinity a to the power 1 by n equal to 1. Yeah. So can you tell how to solve? Yeah, you can take your 2 minutes. You can try. You can try and tell me, or else I will solve.
Can you move a bit upwards in the page?
Sorry.
I have not completed copying the previous sum. Can you
Yeah. Okay.
move
Okay.
a
Yeah.
bit?
Okay. Sorry. Sorry.
Yes, yes, it's okay.
Yeah. This one. Yeah.
Yeah. Okay, sir. Thank you.
Yeah. Okay. Okay. So for the second problem, let's see how we can solve this problem. Okay. So a is greater than
Sir,
0.
here,
Yeah. Tell.
sir, here will be three cases, right? For a equals to 1, for a greater than 1, and for a less than 1.
Yeah. Right. You are right. So any one of the case have you done?
Yes, sir, for a equals to 1, it will be a constant
Yeah, it's
sequence.
trivial, right? Yeah, for any
And for
rest of the.
a greater, yes, and for a greater than 1, we get a power 1 by n greater than equal to 1 for all n. And
Mhm.
from here, we can say that a power 1 by n equals to 1 plus xn.
Yeah.
And from there, like the previous one, by binomial expansion, we can see that it will be greater than equal to 1 plus n into xm.
Yes, yes, right. You are right. Yeah, very good. So whatever you know Sastik, right? So Sastik, you are right. So your way is right. So let me write it down. Okay. So for a equal to 1, obviously it's trivial. So I'm not going right. So for a greater than 1, we can observe that a to the power 1 minus this is greater than 1. So a to the power 1 minus we can write it down as 1 plus xn for xn greater than 0, right? Now we can do the binomial expansion, that is a is equal to 1 plus xn whole to the power n. This is 1 plus nxn plus there are some terms in between and the last term is xn to the power n. So obviously this is greater than nxn, right? So Therefore what? Therefore xn less than n by a. Sorry, xn less than a by n. But someone is trying to join actually. Yeah, xn less than a by n. Yeah. So by Sandwich theorem, this xn goes to 0 as n tending to infinity. Okay. But now since a to the power 1 by n is equal to 1 plus xn, and as xn goes to 0 as n tending to infinity, so the sequence a to the power 1 by n goes to 0 as n tending to infinity. Yeah, so in this way you can prove this. Okay, so this is greater than 0. And as Swastik has mentioned that there will be three cases. So what about the case a less than 1? So in a less than 1, we can choose a b to be 1 by a. So then in b greater than 1. Now once again, someone is trying to join it. So b less than 1. So basically then b to the power 1 by n is equal to 1 by a to the power 1 by n. Now since b greater than 1, so b to the power 1 by n goes to sorry, here a to the 1 by n goes to 1. So b to the 1 by n goes to 1 as n tending to 1. So this limit n tending to 1, 1 by a to the 1 by n equal to 1. So limit n tending to 1, a to the power 1 by n is equal to 1. So in this way we can prove this. For a less than 1, this limiting value will be 1 also holds. Okay. So anybody has any problem in this? I mean, any confusion or doubt in this solution? Tell me. So for the next problem once again. Yeah, that exponential. Anybody? Any problem? Yeah, this question. Probably someone has drawn message. Let me check. Well, so I think nobody has any problem. Okay, so let's come to the next question. So the question is that this type of question is very much useful, and this type of question can come in your final examination also. So consider the following sequence un. Un given by, it's a recursive sequence given by un plus 2 is equal to un plus 1 plus un by 2 for all n greater than or equal to 1. Yeah, so this type of and given 0 less than u1 less than u2, then show that so we need to show that the sequence un or just 2 u1 plus 2 u2 by 3. Okay, so this is the first non-trivial problem, I think. Okay, so let me give you some kind of hint. Okay, so just there is some kind of basic intuition I need to develop. So this is u1 and u1 less than or, so this is u2. Now observe that u3 is actually the average of u1 and u2, so u3 will lie in between of u1 and u2. Now u4 is average of u2 and u3, so u4 is here. u5 will be between u3 and u4. So just again u6 will be between u5 and u4. So just observe one thing, that u1 is greater than u3 is greater than u5, and u sorry, it's more less than 1. So someone's trying to join actually. And sorry, u1 less than u3 less than u5, and u6 less than u4 less than u2. Okay, so well, if you know the concept of subsequence, you can actually realize that these two corresponding subsequence of the corresponding odd indexes and subsequence corresponding even index will converge to some point between u5 and u6. Okay, well, but since we don't now have the concept of subsequence, so we can prove it directly without using subsequence. So let's prove it. Obviously it's a very tricky problem, so let's see how we can proceed. So given 0 less than u1 less than u2, just one second. Yes. So 0 less than u1 less than u2. Yeah. Just one second. One second. Hold on. So u2 minus u1 is greater than 0, right? So now u3 minus u2, this will be half of u1 plus u2. Okay, this is minus u2, so this will be minus half u2 minus u1. Similarly, u4 minus u3 is equal to half of u sorry. So this is minus half of u3 plus u2 minus u3. This is half of u2 minus u3. This is minus half of u2 minus u1. Okay. Now similarly, the next term will be u5 minus u4. This will be what? This will be half of u4 plus u3. u4 plus u3 minus u4. So this will be what? This will be,
This is what we call difference equation.
yeah, no, this type of problem is known as Taylor sum, or Taylor sum. This is not the difference equation. Okay, it is known as Taylor's telescopic sum. Okay, so it will be minus half to the power 3 u2 minus u1. So in this way we can finally see that un minus 1 is equal to minus half to the power n minus 2 into u2 minus u1. So u1 minus un is equal to what? It will be equal to u2 minus u1 into 1 plus minus half plus minus half square plus dot 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 plus minus half to the power n minus 2. This will be what? 2 into u2 minus u1 by 3 into 1 minus half to the power n minus 1. So basically this converges to 2 by 3 into u2 minus u1. Okay, so basically this is the nothing but the sum of all these. Okay, so what we get that the sequence un minus u1 goes to 2 by 3 into u2 minus u1. So this implies what? Un goes to 2 by 3 into u2 minus u1 by u1. So this is what? This is equal to u1 plus 2 u1 plus 2 u2 by 3. Okay, so yeah, that's it. So hence the sequence un goes to u1 plus 2 u2 by 3 for all n greater than equal to 1. So in this way you can prove it. Okay, so in this solution, does anybody have any confusion, any question or any doubt? Ask me. Well, let me just repeat this, the whole process again. The process is fairly very technical. So first u3 minus u2 has to be written in this form. Then u4 minus u3 has to be written minus half square u2 minus u1. Then dot dot dot, the same thing can be written for un minus 1. Then we can do the summation. After summation we get un minus u1 and we find we can get its limit. Okay, so then we are transferring u1 to the right side. That's it. So in this way you can solve this type of problem. So anybody have any issue, tell me. Okay, I think there is no issue. By the way, can I go to the next page, or has everybody done the copying?
Sir, can you just scroll up one?
Yeah, sure. This much?
Sir, a little bit.
Yeah.
Okay, sir, done.
Yeah. So there is another question, which is that so the question is, we have a sequence xn whose all terms are given by an plus bn whole to the power 1 by n for all n belongs to n, 0 less than a less than b. We need to show that limit xn equal to b. Once again, someone is trying to join. So how to solve this type of problem? Well, this type of problem is actually technical as the previous one. So let's do it. So now observe 0 less than a less than b is given. So basically a by b less than 1. Okay. So now we what we want to use, that this limit a by n to the a by n to the power, sorry, a by b to the power n, this goes to 0. We want to use this. Okay. So I mean, we can write xn as follows. Xn is equal to an plus bn to the power 1 by n. So we can take b out. So this is b of a by b to the power n plus 1 whole to the power n, right? So now observe that this a by b to the power n plus 1 is greater than 1. So this x n, so this xn is greater than 1. Okay. Sorry, this xn is greater than b for all n. So again observe one thing, since 0 less than a less than b, hence 0 less than a to the power 2n less than b to the power 2n. I mean, we actually don't really need 2n. It is only, we only need a to the power n less than b to the power n. Okay. So basically a to the power n plus b to the power n less than 2b to the power n. Wait, I need to check. Someone is trying to join it. Okay. So now and now since xn is equal to a to the power n plus b to the power n whole to the power 1 by n, so this equation together implies xn less than 2 to the power 1 by n into b. Okay. So what we have seen, we have this equation and this equation. So together we can prove that this, we can write it as like the b less than xn less than 2 to the power 1 by n less than b. Okay. Now since limit 2 to the power 1 by n equal to 1 as n tending to infinity, so limit xn equal to b. Okay. So in this way we can show that this limiting value of xn equal to b. So obviously it's a very technical solution. So anybody have any issue with this solution? Tell me. Sorry, ask me.
So what would happen if you take a common from the beginning?
Well, the point is then actually the thing is we want to use the fact that a to the power n b less than a by b whole less than 1. This imply, I mean, we actually want to use the fact if r less than 1 then r to the 1 goes to 0. Now in order to use, we actually took b out of this whole bracket. That's why we took out b. There is, I mean, we can take a out, but nothing will happen because the b by a is actually greater than 1. So anyway b by to the b by a to the power n will go to infinity, right? So it will give nothing such remarkable thing. That's why we need to take a out of the bracket. That's why, sorry, we need to take b out of the bracket. Okay.
Okay.
So yeah, there another kind of problem says that we have a sorry. So so let we have a sequence un defined as follows. u1 is equal to root 2 and un plus 1 is equal to root over 2n for all n belongs to n. So prove limit un is equal to 2. So this is also a technical solution. So let's see what in any step, if you anybody get any confusion or doubt, please ask me, okay? Because these type of problems are actually very much technical. By the way, just let me know one thing, am I going very fast? Anybody, am I going very fast?
No.
Sorry.
No, sir, it's fine.
Okay. So we need to show that limit n to infinity un equal to 2. Okay. So So it's a, I mean, it's like a iterative kind of solution, like the previous two problems. Okay, so u1 is equal to u1 is equal to 1 by 2. E2 is given as root over 2 u1. So this is root over 2 root over 2. So this is 2 to the power 1 by 2 plus 1 by 2. Okay. So this is nothing but, I mean, value it. Now u3 is what? u3 is equal to root over 2 root over 2 root over 2. 2 to the power half plus half square plus 1. 2 to 1 by 2 to the power 3. So similarly, what will be un? Un will be 2 to the power half half square plus 1 by 2 to the power n. This is what? 2 to the power 1 minus 1 by 2 to the power n. So this goes to obviously 2 as n tend to infinity, since this 1 by 2 to the power n goes to 0 as 1 by 2 to the power n less than 1, right? So this sequence even goes to 2. So I mean, so this is what we want to show, right? So is this solution okay to everybody, or any step do you have any issue? Just tell me. Okay, so I think the solution is okay for everyone. So what are the next question? Wait, 1 second. Well, just tell me one thing. Do you have any idea of the modern convergence theorem?
No,
Anybody?
sir.
Okay, so you don't have modern convergence. So once again, okay, sir, we'll do it. So the following problem. Well, since it's more than 1 hour, so as I've said at the starting, that if you have any issue with your personal doubts or personal, you can ask me right now. I can solve. So anybody have any question which you were stuck? Okay. Anybody? Any questions which you have stuck already? Okay, so it seems that there is no question. Well, so okay, let's go with the next problem. So the problem is that, once again, yeah, the question is that we are given a sequence un to be greater than 0, okay, for all n, and we are also given limit nth power of un, this is equal to mu for mu greater than 0. So prove that nth root of this thing is same. So we are given UN to the sequence of positive real numbers, and nth root of un is mu. It is given. We need to prove that nth root of the sequence n plus 1 into un plus 1. This is mu. Now how we can prove it? Anybody? Okay, so let me prove it. Once. Now, since we have already given that nth, I mean, no, I mean, look, the thing is, nth root of n plus 1 can be written as like this: n plus 1 to the power 1 by n plus 1 to the power n plus 1 by n, right? Now, we have already seen that limit n tending to infinity, n to the power 1 by n is equal to 1. So, limit n plus 1 to the power 1 by 1, it is equal to 1, right? So, and as n plus 1 by n, this goes to 1 as n tending to infinity, and n plus 1 to the power 1 by n plus 1 equal to, I mean, this goes to 1 as n tending to infinity. So, n plus 1 to the power n, this goes to 1 to the power 1, this is equal to 1. Okay, so we're going to the next page here. So so what we have seen, the limit nth root of n plus 1, sorry, so in the limit nth root of un plus 1, this is equal to un plus 1 to the power 1 by n plus 1 whole to the power n plus 1 by n. It's a fancy way of writing the same thing. Okay, that's it. And as limit nth root of un is equal to mu, so limit un plus 1 to the power 1 by n plus 1 is equal to mu. Now, since that n plus 1 by n goes to 1 as n tending to infinity, and as we have given that un plus 1 by 1 plus n plus 1 goes to mu as n tending to infinity, so un plus 1 to the power 1 by n goes to 1. It is not 1, sorry, it is basically mu to the power 1, this is equal to mu as n tending to infinity. So we can taking product, by taking product n plus 1 into un plus 1, nth root goes to 1 into 1, which is 1, as n tending to infinity. Okay, sorry, it is not 1, it is mu dot 1. So in this way you can, I mean, so hence we are done. So this is what we want to put, right? So I understand that this problem is a bit technical, but if anybody have any query or any confusion at any step, please ask me. Okay, because I feel that in this problem I'm a little bit fast. So anybody have any confusion, ask me. For 2 minutes. Okay.
Sir,
Yeah.
sir, I have a doubt from the assignment.
Well, but the point is we are instructed not to solve the assignment actually. You can ask anything except assignment. We are instructed not to solve anything from assignment. Okay. Hope you understand. So let me go. So another kind of problem. So yeah. So there are one two problems. So I'm moving forward to another problem. The problem is that show that n plus 1, this goes to 1 as n tend to infinity. So how we can prove this? Well, the thing is, this problem can be solved as the same trick that we have done in the previous problem. Okay, so just can anybody want to try out? I'm waiting for 1 minute. Just try it out and tell me if you have done any way out to solve this problem. So let's solve it. So wait, look, that n plus 1 to the power 1 by n can be written as n plus 1 to the power 1 by n plus 1, okay, whole to the power n plus 1 by n, right? Now we have seen that n to the power 1 by n goes to 1 as n tending to infinity. So n plus 1 to the power 1 by n plus 1 goes to 1, of course, at infinity. Okay. Now observe n plus 1 by n. This is what? This is 1 plus 1 by n. This goes to 1 as n tending to infinity. So n plus 1 to the power 1 by n plus 1. This goes to what? Where? This goes to 1 to the power 1 equal to 1 as n tending to infinity. Okay. So in this way you can solve this type of problem. So there's another problem I think I need to solve. Well, let me see. So, oh shit, once again. Sorry. So everyone understood this problem? Does anybody have any confusion at any step? Just tell me. So, so let's go back to the go to the next problem. This problem is saying what? This problem is saying that yeah, show that n plus 1, its nth root is equal to 1, its limiting value. Yeah. So can anybody no, want to try how to, when you can try at least. Anybody? See, the ways are not very much different, but obviously it's need some kind of practice in order to solve this type of questions. Okay. So from previous problems, can anybody guess how to solve this problem? Well, so no issue, let me prove it. So n to the power 1 by can be written as what? N to the power 1 by n. Same trick, whole to the power n by n plus 1. Now we've already seen that limit n to the power 1 by n equal to 1, and obviously limit, it's not obvious, I mean this limit n by n plus 1 equal to 1. So this is n by n plus 1. This is equal to n by 1 plus n into 1 by 1 plus n by n plus 1. This goes to 1 to the power 1 as n. So hence this will be equal to, this is equal to 1. So uh, so now is this okay to everybody? Any step, any issue? Well, there is another question. Well, I think everybody is fine with the solution. Okay. So yeah, with the following, now comes the following question. So assume that limit n tend to infinity 1 plus 1 by n whole to n is equal to. Well, actually, you don't need to assume, but the thing is, it can only be proved after the modern convergence theorem. Okay, but since we have not done this yet, so we can't use this. That's why we need to assume that this limit will be e. Okay, and you might know that value of e will lie between 2 and 3. Okay, assume that this, then prove that, show that n plus 1 to the power 2n by n square plus 1 to the power n is equal to e square. So can you tell me how to approach this? Well, this type of problem are all kind of similar problems. You need somehow used to use, I mean somehow you need to use some kind of trick so that you can use some kind of limit of the some known type of uh, functions. Okay. So can anybody tell me how to approach this type of problem? Okay, let's. So observe one thing, that n plus 1 to the power 2 n by n squared plus 1 whole to the power n. This is nothing but, this can be written as 1 by 1 plus n to the power n whole square by 1 plus 1 by n square whole to the power n square to the power n by n square. Okay. Now observe that this thing has been given to us. Okay. Now since 1 by 1 plus n to the power n, this goes to e. So obviously 1 by 1 plus n square to the power n square, this goes to e. Now observe n by n square, this is nothing but 1 by n goes to 0. So this sequence n plus 1 to the power n by n square plus n whole to the power n, this goes to uh, e square by e square to the power 0. So which is nothing but e square. So finally we get what? This sequence finally converges to e square. So in this way you can solve this type of problems. Okay. So does anybody have any confusion in this type, in the solution? Please tell me. Let me find another type of problem. Well, so there is another type of problem. Once again. So there is, well, let's solve some another kind of problem, which is other than the sequence. Okay. So, um, so what is the set? What will the set union n belongs to capital N 0 comma n be? So can anybody guess what will the set be? This.
Natural number. Natural number union 0.
Yeah, you're right. Yeah, very good. And what will be intersection n belongs to z plus 0 comma open interval 1 by n? Anybody?
0. Only 0.
Wait, why? Why?
Because left ending point is 0 always. It is same for all the sets or n, and it is continuously decreasing towards 0 all the sets after we
Yes,
put the value of n.
you are right. Well, so yeah, it is intuitively clear, but in mathematically, what is the main theorem or main formula you are applying? Well, so it is nothing but the Archimedean property. Well, so do you aware of this Archimedean property?
Yes.
Yeah. Okay. So I mean, if we choose any x not equal to 0, if we assume that x belongs to this whole intersection 0 comma 1 by n, then obviously x, sorry, 0 less than equal to less than 1 by n for all. Okay, but this can't happen due to Archimedean property, right? Right, because Archimedean property says of what? Says that since 1 went arbitrary, so we can choose a m which is actually less than x for some m. So this intersection only contains 0. Okay, so in this way we can solve this type of problems actually. So well, one second. Wait. So let's tell you one thing. Well, this is another application of Archimedean property. This question says that suppose y greater than 0 and y is a real number. Okay, I mean greater than 0 is obviously a real number. So here exists m belongs to n such that 0 less than 1 by 2 to the power m less than y. So it's another application of Archimedean property. Can anybody tell how to solve this type of problem? Anybody? You can think it as Archimedean property, or you can solve this using the concept of sequence. Anybody? Anyway, so you can solve it like follows. So consider sequence 1 by 2. Okay, obviously this sequence goes to 0. So by the definition of the convergent sequence, mod 1 by 2n minus 0, this is less than y for all n greater than equal to m for some m. So we can put here m, putting n equal to m, we can say what, 1 by 2 to the power m less than y. Hence we are done. This is what we want to see, right? So these are very small problems, but trick of course. Okay. So do you know about supremum infimum? Has it been done in the class? Anybody can tell? Anybody can be? Has supremum infimum, this concept has been done in the class? Anybody please tell?
It is in the second week.
Okay. So has already it been done in the class, or you are going to learn it?
Done in the second lecture.
Yeah. Okay. Okay. So one second. Okay. So consider the set A is equal to open 0 comma 1. So what will be the supremum? And what is the infimum?
Smallest upper bound.
Yeah.
Supremum of A is 1, A, and infimum of A is 0.
Yeah, okay, you are right. How to prove it?
From the definition of supremum, we can say that uh, for any x, zero, numbers between 0 and 1 is less than x.
Sorry, can you please repeat?
We have to choose any x that is greater than which is actually not in the set 0 comma 1 from the definition of supremum,
Yes, yes.
and which must be greater than for all elements in between 0 and 1.
Yes, right. Yeah, then, Shwam, then what to do?
Then we can show that that's how actually we can show that supremum of A is equals to 1.
Yeah, you're right. You're yes, correct. Okay. So first, in order to show one is a supremum, observe that one is an upper bound. Okay. So we need to show that one is the least upper bound. That's what is remaining to show. One is least upper bound. Okay. So assume that there exists x which is less than 1 and x is an upper bound of capital A. So x is less than 1 but x is upper bound of capital A. But then observe that this point x plus 1 by 2, this point belongs to capital A, right? And it is greater than 2, so x clearly can't be upper bound. So 1 is least upper bound. So in this way we can see that it in upper bound is 1. And similarly, in exactly the similar way, we can show that 0 is the infimum or the greatest lower bound. Okay. So one second. So yeah. So there is another problem. So S B bounded subset of R and T non-empty subset of S. Prove that infimum S, sorry, prove that supremum T less than equal to supremum. That is, moral of the story is T subset of S, then corresponding supremum will be a very beautiful U. So how we can prove it? Anybody? Anybody?
So give us some time.
Yeah, yeah, sure, sure.
So can I say?
Yeah, yeah. Tell.
So from the question, it is given that T is a subset of S. So
Yeah.
we can say every element in T is contained in S.
Yeah.
Now I am taking that S as given S is bounded. So we can take that S is bounded above also.
Yeah, right.
So I am taking suprema. So from the LB property, supremum of S does exist, and supremum of S is equals to I am taking some capital M,
Yeah, right.
and also and as also T is a subset of S, we can say T is also bounded subset.
Yes, yes.
So I am taking that number supremum of T as some small m.
Yes.
So like that way, we can say that that supremum of S is also an upper bound of T. Like that way, we can say that supremum of T is less than is equals to supremum of S.
Yeah, right. Very good. So, what he told that supremum S is an upper bound of T. So, supremum T less than equal to supremum S. So, in this way, you can do this. Okay, very good. Now, there is another kind of problem. Once again. Yeah. So, let's come back to the sequence. Let's say it's the one problem. So, so find the limit of consequence 1 by n plus 1 and whole square plus 1 by n plus 2 and whole square plus 1 by n plus n whole square goes to 0 as n tending to infinity. So, can you tell me how to solve this type problem? It's a application. I mean, of course, some of you can guess probably that it's a application of the sandwich theorem. So, can anybody tell? Anybody? Okay, so let me don't wait. So now observe that any for any m belongs to m, 1 by m plus n, obviously m greater than 1. This is less than 1 by n plus 1, right? So 1 by n plus 1 whole square plus 1 by n plus 2 whole square plus 1 by n plus n whole square. This is less than what? This is less than n by n plus 1 whole square, right? This is one side, this is part 1. And for the second part, what we need to do? We need to do that, observe that 1 by n plus m, it is anyway greater than 1 by n plus n for all m, right? So 1 by n plus 1 whole square plus 1 by n plus 2 whole square plus 1 by n plus n whole square. This is greater than 1 by, this is greater than n by n plus n whole square, right? So now if we put this whole term to be un, so this equation 1 and 2 together gives that n by 2n whole square less than un by less than un plus 1 whole square. Now this goes to 0 and this goes to 0 and n tending to infinity. So by sandwich theorem, limit un goes to 0. Okay, so this is another type of trick in the sandwich theorem. Okay, so yeah, that's enough for today. Okay, so now I am stopping the session here. So if you have any issue or any doubt, you can ask me in the next week, this same Friday. Yeah, same Friday. I'm going to take the live session again. Okay. So any problem or any confusion in this live session, you can ask me on the next Friday. Okay. So I'm stopping the meeting. Okay. See you in the next coming Friday.
Thank you, sir.
Thank you.
Thanks, sir.
Thank you.